Alright, so I have not yet graded the exams. Those will probably be finished, I'll do it over the weekend, I think. So we'll go over the solution together Monday next week. But looking to the future, the next homework assignment you have, number 7, that's available now on Blackboard, and it has both some problems related to channel geometry and also a beginning idea that you're going to need to use on project phase 3. Just wanting to get you to do a little bit of advanced work to put towards the project. Now, on that subject of the project, the first phase is due on Monday, March 22nd. The first phase is that one where you're looking at the map of the area that you've got, and you're determining the characteristics that allow you to calculate the water demand. So phase 1 is estimating the demand. At each of those green arrows, you're going to have to supply water. So for instance, in the north zone, there are residential demand and commercial demand, which are split between the flow at A and the flow at M. You're going to have to go through and do some calculations and make assumptions to figure out how much water do they need at the sports stadium. So think about, how is water used at a sports stadium? It may be a little bit different than residential demands, where the sports stadium, maybe all of the demand is concentrated into a period of just a couple of hours. Or maybe if you think about when the water demand is, it might be concentrated at a halftime. So you're going to have to just make reasonable assumptions and find data online, and you could use the data that I've provided in that PDF file that's on Blackboard as a basis for starting. But that is Monday, March 22nd. And remember, what we need for phase 1 is your calculations and supporting assumption details, and it should be summarized on the PDF that I've given you, that demand summarization table. Now we're moving on to chapter 10 in the textbook. This is another figure that is on that homework assignment you're going to be doing. And so on that homework that's due next Monday, what I'm going to have you do is assume that the peak flow is 560 liters per second. So that means this maximum day for the year at the highest demand that they have during the daily cycle, that is 560. And so what I ask you to do in that homework assignment is, if you know this is 560, what's everything else? And you can scale it using the percents that are on the vertical axis. All right. So this is just an example syllabus to make a point about the course. Like in the first part of the course, the study that you were doing and all the procedures that we were learning are kind of tied around determining pressures and flow rates in the pipe. In the next part of the course, we're moving on to open channel flow, and so that means that we're no longer fixating on closed conduit or pipe flow, but in this new open channel section of the course, we're going to be looking at calculations that allow us to predict what is the water depth or flow rate of water through a river with certain characteristics. If we know how wide the river is and the depth of flow, then we could calculate the flow rate Q. Or if you know the flow rate and the width, you'd want to know what depth will it be flowing at. And these are important calculations for reasons related to flooding, for example. That's a real recent important illustration of why knowing the flow depth is critically important, is because you need to know whether to put in the gates to the flood wall, for example, or you need to know how high is the creek going to rise next to a home, and whether the people should evacuate during a certain flash flood. So that's what we're going to be moving on to. Now, those are the specific content and kind of discipline of hydraulics type applications, but in the entirety of the course, what I'm hoping that you learn includes self-directed education, like teaching yourself a procedure. I try and make some of the examples pretty to be a pretty good indication of what you'll need for the homework, but there's going to be a few cases where you have to go into the book and figure out what to do by an example that's in the book, or understand the definition of a term by what's in the textbook. So teaching yourself to learn will really come into play with the project. And so another part of what I want you to take away from this course is doing a project in phases and breaking up something difficult into smaller, more manageable pieces. And if you're prone to procrastination like I am, that's really the only way to make progress without just pulling all-nighters and doing a bad job because you're rushed, is you have to break a project into pieces and then give yourself a deadline. I also want you to learn the iterative design process, and maybe some of you have taken classes already where you did a little bit of design, but for many of you this may be the first project where you're really moving on from learning engineering fundamentals to learning the application of engineering fundamentals and applying the design process, and learning how to use some of the design software like the EPA net, for example, and then just the characteristics that an engineer needs to get through a career of grit, determination, staying focused and resilient when something is intellectually difficult. So these are maybe the soft skills that don't tie into whether you can calculate the depth of a hydraulic jump or the pressure loss in a pipe, but these are just as important as the technical skills as well. Well, let's talk about open channel flow, and we've addressed some of these topics before when we were in fluid mechanics together last semester. And I hope you remember the discussion we had last semester on different types of flow, because that comes back into play again this semester as well. When we were breaking it up into categories, we classified flow partly on whether it was uniform or non-uniform. So remember that non-uniform flow has a convective acceleration equal to 0, but uniform flow has no convective acceleration, but non-uniform flow does have an acceleration. It may be changing the magnitude of the velocity, like here in figure A, where the flow is speeding up as the diameter of the nozzle contracts, or it might be changing the direction component of the velocity vector. Either one, non-uniform flow is where there's a change in velocity with respect to position. So that's one category of flow types. And what causes that acceleration? What type of acceleration causes non-uniform flow? It's convective acceleration. Now, local acceleration is what causes unsteady flow. So steady flow is when over time the stream flow patterns and the velocities are constant. Unsteady is where it's changing over time. So the acceleration type that causes unsteady flow is local. And I've got a picture here of a before and an after of a culvert failing. In this picture, what happened was that the water level was rising on the upstream end of the culvert. So the water can't flow through its normal creek that used to be there because they put a road in on top of the creek. And a barrel of a culvert was in place to pass the water, but when there was a lot of water flowing through this creek, the water level rose on the upside end of the creek, and that created a seeping pressure that caused a scour and piping of the soil particles that were around the culvert. And so they packed soil around the culvert, and of course water was flowing through the opening of the culvert, but water was also seeping through the soil itself, and that can undermine the soil and reduce its strength. And so that's kind of what happened here, is that culvert eventually failed and collapsed in on itself. And so that's an example of unsteady flow. You can't just with a single image see unsteady flow. We have to have a series of images over time to understand unsteady flow. And let me show you another video of unsteady flow. This is from the island of Crete. Let me pause the recording for just a moment lest we get a... It's also unsteady flow. The flow around that hydraulic structure is going to be very different when one of the piers supporting it collapses into the river. So the effective cross section would have changed. So these are different flow types: steady versus unsteady, uniform versus non-uniform. We can also classify the channels that water flows through. And a prismatic channel is one that has a constant cross-sectional shape. The slope is constant and it's regular. And so a prismatic channel is one that's most likely been engineered. It could be a trapezoidal cross-section, it could be rectangular, but if you're going to draw a line down the middle, it would be mirrored along the center line. And so from the side view, you can see it has a nice even slope, and the only way that you'd have such a constant slope like that is if it's an engineered material like a paved asphalt liner on the bottom, or if it's concrete. It would be very unlikely to see a constant channel slope if it was a combination of soils and rocks that differentially scour. And a prismatic channel from the top view would be relatively straight. You see a lot of prismatic channels in Florida. If you fly over Florida, there are really long canals that have been dredged and put in to help with the drainage. And so you can sometimes, even from above, differentiate between a prismatic engineered channel and one that was natural. So non-prismatic channels have more variability. And so the cross-sectional view, rather than being a mirror image along the center line, for a non-prismatic channel it would be irregular because there are just differences in the strength of the soil underneath the water line, and as the water is flowing, it will pick up and carry downstream the soil that's going to scour and erode the most easily, and what stays behind is the soil or the rocks that are more resistant to scour. And so this little outcropping in the bottom of the channel, it's not coincidence that it's there. There's something about that outcropping that was able to resist the shear stress that was applied by the water on the bottom of the channel as the water was flowing. It might be a bit of rock or some really cohesive clay where everything else was sand, or maybe a looser loam. Likewise, from the side view, in a non-prismatic natural channel, you'll see some parts of the stream may be really steep, others that are relatively flat, and then from the top view there's irregularities in a non-prismatic channel. There's a table in your book that I want to bring to your attention, table 10.1, and this is really important because it has some useful formulas to allow you to calculate. Some of them are pretty easy. You know, like for a rectangular channel, the area is quite obviously the depth multiplied by the width of the channel. But it's less obvious for some of the other shapes, like a parabolic section, for instance. The cross-sectional area of a parabolic section is 2/3 the top width of the channel multiplied by the depth y. And so for each one of these different shapes, we have the formula for the cross-sectional area, the formula for the wetted perimeter, and the wetted perimeter is the length that water is in contact with in the cross-sectional view. So like for this rectangular shape, at the top, that isn't counting in the wetted perimeter because the top is in contact with air. But on the sides and the bottom, that is part of the wetted perimeter. So the formula here, B is the bottom width, and then 2 times y is because it touches on the left side and it touches on the right side. And so now look at the formula for the trapezoidal channel. For the wetted perimeter, they're saying it's the bottom width, of course, and then the length of these side slopes. The side slopes are inclined at a 1 to t angle, and I know you've seen that before. We did a little bit of just introductory trapezoidal channel geometry, and I showed you that we defined these side slopes as one unit of vertical rise and t units of horizontal distance. And so with that side slope being defined, then you can find the length of the side of the channel with this formula for W. So 2 times Y times W. So all of these different shapes, you can find the wetted perimeter distance. Hydraulic radius, remember, is the area divided by the wetted perimeter. Top width, capital B. Sometimes it's the same as the bottom width, like a rectangular channel. Trapezoidal, it's different because you also have some distance associated with these side triangles. And so it's the bottom width plus 2 times whatever this distance on the edge. So I wanted to point out this table to you, and that it has a wide variety of different geometries, including for the parabolic section. Flow classification. We've talked about laminar versus turbulent flow, right? Where laminar flow is when the Reynolds number is less than 2,000. Turbulent is where the flow, the Reynolds number of the flow is more than 4,000, and in between is transition. So within turbulent flow, we can further break that into 3 different subcategories. And this cross-sectional view, what we're looking at here is a velocity profile. So the water is flowing from the left towards the right, and this red line represents the magnitude of the velocity. And the idea I'm trying to convey with this is that the velocity of water flowing through a river is higher at the surface than it is down at the bottom of the channel. You know, where the resistance is being applied by the channel to the water. Down here at the no-slip condition, where there's shear stress applied by the mud, or if it's a concrete line channel, whatever stationary and unmoving is applying a resistance to the water as it flows. And so the velocity is 0 at the interface of the solid and the liquid, but then the further away you get from the bottom of the channel, the velocity speeds up. So we're going to say that there is a laminar sublayer. Remember, we've talked about that already this semester, the idea that even when in general, if you have your average velocity for the flow, maybe most of the flow is turbulent, but there will be a layer down near the bottom of the channel where you have a laminar zone, a laminar sublayer. So the categories of turbulent flow are that either these roughness elements are fully contained within the laminar zone, and we call that smooth turbulent flow. That almost seems like a contradiction in terms, doesn't it? Smooth turbulent flow. But what we mean by that is that, you know, whether it's concrete or whether it is pebbles, whatever, the water's moving slow enough that these projections of the roughness elements are fully submerged in the laminar sublayer. So that's smooth. Transition is when the laminar zone is exactly the same height as the roughness elements, and then rough flow, they project outward into the turbulent zone. So rough turbulent is where the roughness elements have even more of an effect than they otherwise would if they were inside this cushion of the laminar sublayer. Now, there are just a couple of equations that are really important in open channel flow. And we'll spend most of the rest of the semester just using these few equations. And I wanted to spend not a lot of time, but a little, talking about the basics and where these equations come from. And so if we start with the force balance on some element of water, what we're looking at in this sketch is the cross-hatched shape, or I guess not shape, but the cross-hatched shading is meant to represent the bottom of a river. Logan asks a question, is that like the rapids versus smooth flow of the Ohio River? Yeah, I think that's probably a pretty good analogy. You know, if you have really slow moving water, then you may have a pretty thick laminar zone. Okay, so this side view, this is the bottom of the river, and we're going to do the control volume approach, where you take a certain element of water, and so this is the water surface. See the triangle and those little crosshatches there that is meant to invoke the shimmering ripples of an open surface in contact with the air. So you've got a water surface, and you can see that the depth is decreasing in the direction of flow. So the reason why they show that is just to emphasize the point that this equation can apply whether you have uniform flow or non-uniform flow. The same force balance can be done. And here, the depth of flow is decreasing in the direction of flow. So see how the depth is getting shallower and shallower? So what we're going to do is a force balance. And so consider all of the forces that apply to some element of water. So the water inside the dashed lines, let's look at what's happening with that system. The weight of the water is acting downward. And so the weight of the water will be the unit weight. So unit weight would be newtons per cubic meter. The area is the cross-sectional area. And so if we were looking at it from the front, then we would have some cross-sectional area. For instance, if it was a rectangular channel, then we'd have the depth multiplied by the width in order to get A. So A is, we can't see it because it's into the page, but there's an area there. And then delta X is some distance between control point 1 and control point 2. So it's essentially the volume. A times delta X gives you the volume of this element of water, and then gamma multiplied by the volume gives us the weight of the water. So that acts downward. And there is a hydrostatic pressure distribution on the left that's related to how deep it is. And so notice how it is a linear increase in the pressure. And that's because pressure is unit weight times depth. And so the pressure increases at the rate of the unit weight. So the pressure is pushing this element of water to the right at surface 1, and it's pushing to the left at surface 2. And since it's not as deep at location 2, then that means that the hydrostatic force pushing to the left isn't going to be as great. And then there's a resistance to its flowing downstream, the shear stress multiplied by the perimeter. So P is the perimeter that is into the page, and then delta X is that distance between 1 and 2. So we get an area from P times delta X, and then multiply that area by the shear stress gives us a force. And so this is just a force balance. And because the force balance is, there's less force at 2 than there is at 1, this is moving to the right. So the governing equations that we're going to apply this semester, continuity will continue to be very important, where what we could do is we could do a balance between the flow rate in and the flow rate out at 1 versus at 2. And so there can't be any accumulation here if we have steady flow. So if this is non-uniform but steady, that means that the depth is constant over time, then that means that A1 V1 has to equal A2 V2. So even though maybe the velocity is faster at 2, the flow rate is the same because the depth is less. Okay, so continuity will be one of the tools we use this semester, and then the other is different equations that are derived from the momentum equation. And so in momentum equation, what we're doing is we're looking at the imbalanced forces. And since we have a difference in velocity between the flow in and the flow out of the control volume, the momentum equation can be rearranged to allow us to calculate the magnitude of the shear stress that's applied. So the shear stress is related to the slope of the energy grade line, S sub F, and the relationship between the shear stress and the Darcy-Weisbach equation that we learned in closed conduit flow still applies in open channel flow as well. It's just that it's not common for us to apply the Darcy-Weisbach equation in open channel flows. We don't usually calculate F values for open channel flow. Instead, we use a different equation for flow resistance. We use the Manning equation. But continuity and momentum are the big ones. Now remember, EGL is the energy grade line, and here we have the hydraulic grade line is the water surface, but the energy grade line would be above the water surface, and it would be above it some distance that's dependent, that's calculated by the v squared divided by 2g. The velocity head is how high above the water surface the EGL is. Okay, so whereas when we were working with pipes, we used this energy equation. So in a pipe, you can have a pump, and the losses were differentiated into the friction losses and the local losses. This was our energy equation if we had a pipe. In open channels, things are a little bit different. So the pipe was enclosed. The open channel is open to the atmosphere. And you can see that I've just suggested that this open channel is inclined, and that's why the water's flowing from 1 to 2. The water flowed from 1 to 2 in a closed conduit because of a pressure difference. In open channels, it flows from 1 to 2 because of an elevation difference. Instead of a pressure head in the energy equation for open channel, we'll have the depth. So we will no longer calculate the pressure because it's open to the atmosphere. So instead we would have Y1 as the first term of our energy equation in open channel. It still has a velocity head term, and now Z is referring to what's the elevation of the bottom of the channel above the datum. So here the dashed line is our elevation datum, and so Z1 would be the elevation of the bottom of the channel above the datum, and then Y1 takes us to from the bottom of the channel up to the water surface, and then V1 divided by 2G is how we could calculate the height of the energy grade line. So there are some subtle differences, and another is that there aren't any pumps in open channels. There may be devices that lift water, physically lift water, but if you've got open channels, by definition it's open to the atmosphere, you can't have a pump because pumps add pressure. The head loss term that we were using in closed conduit flow had local losses and pipe friction. We will occasionally have transitions, like when a channel is getting wider or contracting. If it's getting narrower, we'll have an expansion and contraction coefficients, but we don't have like fittings and valves in open channels in the same way that we did with closed conduits. So we won't have to worry about globe valves and gate valves and calculate the effect of those on energy losses in quite the same way. All right, so continuity, momentum is where we have a relationship between resistance and velocity. Gavin asks if it gets more narrow, does that mean the depth increases? And Gavin, the answer to that question is it depends on whether flow is supercritical or subcritical. And you haven't learned what that means yet, but you will. It's a very strange thing. You'd maybe expect, just like by instinct, you might expect if a channel gets narrower that somehow it's like choking the flow and therefore it would have to get deeper. But sometimes the water will, when you make the channel narrower, it will actually speed up and then it'll get shallower. So it depends on if the flow is supercritical or subcritical. So I'll have to teach you more about that later. It depends is the answer. All right. So I told you that we don't usually have F values for open channel flow. I mean, there technically is a Darcy-Weisbach equation that relates flow velocity and F values in open channel flow, but the Manning equation is far more convenient and gives us a good enough answer so that we can use constant N values rather than variable F values in our calculations for velocity. If you have uniform flow, that means that the slope of the energy grade line, is the same as the slope of the bottom of the channel, and that's the same as the slope of the water surface. So all three of those are parallel to each other. Those three surfaces are parallel if you have steady uniform flow. The energy equation we've just already talked about, and what it all boils down to basically is the head at location 1 is equal to the head at 2 plus the losses. So the head at 2 is going to be less than the head at 1 because of the losses that occur. And when you have uniform flow that's steady, the head losses are equal to the elevation difference between 1 and 2. Okay. So let's get just a bit of practice using this new formulation of the energy equation, where we no longer think in terms of pressure, but now we start thinking in terms of depth. Okay, I've given you both a side view and a cross-sectional view. And we have location 1. We know the elevation of the riverbed is 0.782 meters above the vertical datum. We know the width of the channel is 0.5 meters, and it looks like it's a rectangular channel. And then the average velocity is 0.55 meters per second, and then we know the total energy. So from that, we can tease out what's going to be the depth of flow at location 1 and what's the flow rate. All right, we haven't done the breakout groups for a while. So let me put you into the breakout groups. Hopefully you've got this printed out, these notes. If not, take a quick screenshot, because once I put you into the breakout groups, then you won't be able to see this example anymore. So let me just push to the breakout groups and calculate these two things. What's the depth of the flow and what's the flow rate Q? Start this recording again so that the solution goes into the PDF. All right. So we know E. We've got the velocity and Z. So we're just solving for Y in this one. Okay. Okay. So we know E, the Z, velocity, just rearranging the equation for y1 means that it's 0.654 meters is the depth, if that's how much energy we have. And then once we have the depth, we can find the flow rate by multiplying the average velocity by the cross-sectional area. And the channel, remember, is 0.5 meters wide, so it's the depth times the width that gives us the cross-sectional area, then multiplying that by the velocity is where we get Q. All right, the homework assignment, this next one, homework 7, which is due on Monday, it's pretty easy. It's like questions like that for the most part. It might be one of the simplest assignments of the semester. That's not an endorsement to procrastinate, but I hope that you're not too stressed out. If I remember correctly, those are relatively easy questions. Let's talk about channel slope. In channel slope, the physical length of a channel segment L is different from the top view length or the plan length. If we have a given angle, because this is inclined, you know, the slope, the water's flowing downhill, and between 2 points there's an elevation difference delta Z. So we could do a little bit of trigonometry here and calculate the delta Z based on the angle. And if we did that, the point that I wanted to make is that if you have in channels relatively small angles, you know, a 1% slope would be considered pretty steep. But even for a 10% slope, L and L times cosine of theta are very, very close together. And so we don't usually bother differentiating between the top view length and the physical inclined length of a channel. So, you know, the depth of the channel, the water depth, you would have to, if you wanted to really find the vertical component of that depth, you'd multiply y1 by the cosine of the angle to find, you know, the depth is perpendicular to the channel bottom, and so it would go up at an angle, and the energy equation would just be the vertical component of that. But don't sweat it, is what I'm saying. Because of these small angles, anything less than a 10% slope, which is essentially every flow condition you'll ever encounter, you can just use the depth rather than the inclined component of the depth in order to apply the energy equation. Now, one other thing I wanted to mention, it's the water is flowing downhill, but slopes are expressed with the understanding that we mean downhill. So there's a positive sign associated with the slope. So if I tell you it's a 1% slope, that doesn't mean it's 1% uphill. It just means we don't say minus 1% or minus 2% for these slopes, because the slope is always downhill. In very, very rare cases will you have what's called an adverse slope, where the water is flowing uphill briefly, temporarily, maybe like at a water park or something, where you have water going uphill just as a novelty for a moment. So by definition, downhill slopes have a positive sign. Some of the other ways that we can categorize flow, remember there's uniform versus non-uniform. There is steady versus unsteady. We've talked about laminar versus turbulent. And for open channel flow, we apply the same simplification that we did for non-circular conduits. You may remember that we had a lecture earlier this semester, it was class number 8, where we were talking about how to apply non-circular conduits into formulas that normally we would use d, diameter. So if you have a channel that doesn't have the diameter, you can use 4 times the hydraulic radius in place of it. So you can calculate the Reynolds number, and if the Reynolds number is above 4,000, then that's turbulent flow. So velocity times 4 times the hydraulic radius divided by kinematic viscosity would be the Reynolds number. All right, now earlier I got a question about if you take a channel and choke it down to make it narrower. Somebody asked, does it get deeper or does it get shallower? And I said it depends on whether the flow condition is critical, subcritical, or supercritical. We're going to go into a lot more details later, but because one of your homework problems just asks you to classify the flow regime, what that means is calculate the Froude number. Froude number is something that tells you whether the flow is supercritical or subcritical. And the formula, the most basic formulation of it, there's lots of different formulas depending on whether you know the flow rate or the velocity, or different formulas if you have a rectangular channel or a trapezoidal channel. What you need to know for now is that if you have a Froude number of more than 1, it's supercritical, and you can calculate the Froude number by knowing the flow velocity and then dividing it by the square root of g times the hydraulic depth. And the hydraulic depth is the area divided by the top width of the channel. So if you have a rectangular channel, the hydraulic depth is the flow depth. But if you have a non-rectangular channel, like if it's trapezoidal, then you have to calculate the equivalent depth that it would be if it was rectangular. And so hydraulic depth is the cross-sectional area divided by the top width. So this simple Froude number calculation, you're going to classify whether the flow is supercritical or subcritical for one of the problems on the homework. All right, so that's it for today. Let me just go back to the announcement slide before we break for now. The things that you've got on your plate are homework 7 is due on Monday, and I'd encourage you to start thinking and read through the handout I gave you related to the design project, because the flow estimation and demand calculations are due on Monday the 22nd. That's it for today. Go outside and enjoy some of this nice weather. It's beautiful out there, right? It looks beautiful. I haven't been outside, but I'm going to take my own advice and go for a stroll. Take care, everybody. Bye.